Okay, so what's the plan for today? What do you want to talk about?
Um, I just want to learn like OSPF, and I want to learn more about OSPF and doing, like with redistribution and some of the pitfalls of like, hey, of where you get routing loops because of mutual redistribution.
Vince, can you see my screen shared out?
Yep, I can.
You can. Okay, so right now there's nothing configured here except the basic IP addressing. So let me draw out what your topology kind of looks like. So what nodes would be running what protocols do you want to see?
Like if let's see what we got. Well, it would be like two routers be running to like BGP, and then to two devices running OSPF, and the two, and that would be like router 1 and 3 would be like DR BDR, and then it would be OSPF point to point between like router 1 and router 6 and router 3 and router 7.
Okay, so they're running OSPF plus BGP?
Yeah. So it would be like router 7 and say 6 would be running OSPF and BGP
To each other, you mean?
That could be fine. Yeah.
Like this?
That or to a third router. It's either way. That would be okay. It's just about more about doing the redistribution. Like if you're so on the router 1 of 7 and 6 would be, you were getting BGP routes redistributed in OSPF, and OSPF routes redistributed into BGP.
Okay, so let's run to OSPF back here on the right. And then we'll take the BGP routes in from 6 and 7 to routers 1 and 3, and then we'll do the redistribution here on 1 and 3. Does that sound about right?
That sounds good. Yeah.
Okay, so let me get to configuring. Okay, so let's start on router 5. OSPF, if I could type it, network point to multi-point. And then on 1 and 3. Okay, so router 5 has OSPF routes that are coming in from 1 and 3 over the DMVPN tunnel interface. It doesn't really matter that it's a DMVPN, could be just any link. And then let's run BGP between these 4 nodes over here on the left. So 6 and 7, would these be in the same BGP autonomous system? Do you have multiple peers to the same provider?
It would be 6 and 7 would, yeah, 6 and 7 would be, it would be in the same autonomous system connected to the other end with the same AS on the other end. So it'd be 2 routers on the other end that would be in the same, different than the 6 and 7.
Right.
That, but those 2 would be the same. So you would have, so 6 and 7 would be learning BGP routes, both from the 2 different routers in the same AS.
Okay, so 1 and 3 are peering BGP. Let's peer 6 and 7 together. We'll say they're in BGP 200. So let me write this out.
Yep. Exactly.
Okay, so 6 and 7 are going to run OSPF together plus BGP. And they're peering together with their loopback interfaces. Okay, then 7 is going to peer with 3. So neighbor 155.137.3. Do you want me to email you a copy of this diagram so you can open it in another window or something?
Sure, that'd be great.
Okay, I just sent the email. Okay, so 7 is peering with 3. 3 needs to peer back with 7. Neighbor 155.137.7.
Right, got it.
And then 6 and 1 are going to peer. Do you use viral at all for your studies?
I have viral, I have EVNG, I have GNS3, so I have all of it. So you mostly use EVNG.
Okay, I'm using viral, so at the end
Okay.
I'll save this as a viral file so
Okay,
you
Cool.
can
I have that too.
recap it afterwards. Okay, so from router 3's perspective, it should be learning the loopbacks of 6 and 7. And we're not yet advertising anything the other direction. So let's go ahead and do redistribution. We're going to redistribute OSPF into BGP and then BGP into OSPF. So under BGP 100, we're going to redistribute OSPF 1. Okay, no arguments on it yet. We're going to come back and look at the loop prevention after we do just basic redistribution.
Yep.
And then under OSPF 1, we're going to redistribute BGP 100 subnets. Okay, same thing on router 1. So router BGP 100, redistribute OSPF 1, router OSPF 1, redistribute BGP 100 subnets. Okay, so if we look at router 5, who's running OSPF on the back end, and we look at the show IP route OSPF, we should be learning those two external routes, the 150.1.6.6 and the 150.1.7.7. Okay, notice also that we're load balancing between 1 and 3 because they both have a cost of 1 as they advertise the external prefixes into the OSPF domain. Okay, so let's look at on router 7 and show IP route BGP. We have 1, 3, and 5's loopbacks learned by a BGP. And let's see, can we ping to 150.1.5.5? Excuse me, as we're sourcing from 150.1.7.7. Yes, we can. So we have connectivity between the two domains. So in terms of the loop prevention, what the problem you could run into is that you have these updates coming in as BGP this way. Okay, and these are iBGP, or actually eBGP. So they have a distance of 20. We advertise them this way over to router 3. Assuming that router 3 is learning the same prefixes in this direction, eBGP with a distance of 20, and then it's learning OSPF with a distance of 110, it means that the OSPF routes don't get installed. The BGP routes should be getting installed instead. So this is going to stop us from redistributing back, or basically the route feedback is automatically going to be prevented based on the administrator distance. So if we look at router 3 and look at the show IP route BGP, we should see that 6 and 7's loopbacks are installed as BGP routes as opposed to be installed via OSPF. Okay, we should be learning them for OSPF though. If we look at in the OSPF database, show IP OSPF database, and we look at the type 5 external link states, we can see that there's two advertising routers, 150.1.1.1 and 150.1.3.3, both doing the redistribution. But the issue is that these never make it from the OSPF route or the OSPF database. They never make it into the routing table because of the administrative distance, because 20 is lower than 110. Now, it would be an issue if they were iBGP neighbors, because iBGP is a distance of 200. So we would install the OSPF routes again and then redistribute it back into the BGP process. But just based on the administrative distance, there's nothing that we really need to do in order to stop the route feedback. Now, we could go one step further with this. and we could use some route tags. So we could say that when we go from BGP into OSPF, we're gonna set the tag. Okay, let's say we set the tag to 1 for router 1. And then when we go from router 3 from OSPF into BGP, we could say redistribute basically not tag 1. So it would be everything that's coming except the BGP peering that it's learning from router 6. So it really depends on what's going on. Like if there's a convergence event and they lose some of the routes, it's possible that the route feedback could occur then. So let's say, for example, that we lose this link between 6 and 7. So on router 6, let's go to gig 067 and shut that down. And the same on router 7. Okay, if we look at the show IP BGP now, we should be learning router 6's loopback in from router 3. Okay, so on router 3, let's look at the show IP BGP. And 6's loopback is learned from 155.1.146.6, which is 6's next hop. The issue here is that I didn't advertise the link between router 1 and router 6 into IGP. So I can't use this as a best route. So either we need to do next hop self from 1 to 3, or we need to redistribute those links into the process. So let's go ahead and do next hop self. Let's say under BGP 100, neighbor 150.111, next hop self. And the same thing on router 1 back to router 3. Neighbor 150.1.3, next hop self. Okay, then on router 3, let's ask for a route refresh to clear the table, clear IP BGP star in. And we show IP BGP. And now 150.1.6.6 is coming from 150.1.1.1. Okay, so if we look at what are we advertising from 3 to 7 now in BGP, show IP BGP neighbor 155.1.37.7 advertised routes. We should be advertising 150.1.6.6, which basically we're advertising its own prefix back to the same autonomous system. Okay, if we look at router 7 though, and we debug IP BGP updates, and then clear IP BGP star in, we see 150.1.6.6. It says it's denied due to AS path contains our own AS. So even though technically there's a loop in the advertisement, there's not going to be a loop in the traffic because of BGP's loop prevention mechanism with the autonomous system number. So it's kind of an inefficiency that we're redistributing the route back, but at the end of the day, it's not really going to cause any problems because BGP is going to prevent this with the with its own loop prevention mechanism.
Yeah, unless you had a config for to allow your own AS in, and then that's another problem.
Correct, unless you're allowing your own AS in. Yeah. So let's bring that link back up between 6 and 7. And then let's look at the solution with doing the tags. Okay, so on router 1, we're going to create a route map that is BGP to OSPF. Okay, that says set tag 1. And then we're going to have another route map that is OSPF to BGP, deny 10, match tag 3. Okay, then we're going to permit everything else. Okay, router 3 is going to do the opposite. So it's going to say route map BGP to OSPF, set tag 3, route map OSPF to BGP, deny 10, match tag 1, and then permit everything else. Okay, so under the OSPF process, we're going to say redistribute BGP 100 subnets, use the route map BGP to OSPF. Okay, then under BGP, we're going to redistribute OSPF 100 or OSPF 1, route map OSPF to BGP. Okay, router 1 is going to do the same thing in the opposite direction. So under BGP, we're going to redistribute OSPF 1, route map OSPF to BGP. Under OSPF 1, we're going to redistribute BGP 100 subnets, use the route map BGP to OSPF. Okay, so if we look at the show IP BGP and look at what we're learning inbound, we're learning 150.1.6.6 from router 6 directly. And we should be putting this into the OSPF process with the tag. So if we look at the show IP OSPF database, we see the prefix 150.1.6.6 has a tag of 1. Okay, it also has a tag of 3 because it's coming from router 3. And then 7's loopback has a tag of 1 when it's being redistributed by router 1. It has a tag of 3 when it's being redistributed by router 3. Okay, the difference is going to be here when we now look at the show IPBGP neighbor and then the eBGP neighbor and advertised routes. We're no longer feeding them back that prefix 150.1.6.6. So when it's only one prefix or a handful of prefixes, it probably doesn't matter. But if it's the full BGP table, that's going to be a problem. Just from a processing point of view, you don't want to take in 700,000 routes from your peer and then advertise them 700,000 routes back, which they're eventually going to have to drop anyways. So let's recap the config here. Show run, section route map or router. So we're saying if the routes come from BGP and they're going into OSPF, we're setting the tag to 3. And then under the OSPF process, we're using this route map BGP into OSPF. Okay, so they come in with a tag of 3 in this direction, and they go up to router 1. Okay, then router 1 says the opposite of this. It's show run section route map or router. Says if they already have a tag of 3, then deny them. And then anything else that's untagged or has a different tag number, permit that to go from OSPF back into the BGP process. Okay, then under BGP, we're saying redistribute OSPF 1 route map OSPF to BGP. Okay, so you also mentioned static routing.
Yep.
Does that make sense up to this point so far?
So for the static routing, say for example on router 3, we have a static route, and you're redistributing to OSPF and advertising to BGP, and then on routers on connected to router 7, there's another device that has a static route, and then you're redistributing that static route into OSPF and advertising to BGP. Say the same route, right? When we want to advertise that same route out, both 7 and 3, but we want to prefer 3. And this is actually a real world scenario for me. I've advertised that route, and then I prefer the BGP route advertised out, but then if the primary route on router 3 goes down, 7 advertises the route, but then when the router 3 is back, we still preferred 7. Because I want it to be like when 3 is back, you use that route again. So, static route redistributed to OSPF, advertised via BGP.
Okay, so they're in 2 different autonomous systems, though, 2 different BGP ASs.
Yes, that's correct.
And
So
then they have a
AS200
connection.
would be advertising the route, and say AS100 would be advertising the route out to both each other and to the rest of, say, a BGP network.
Okay, why do they have overlapping routes between 2 different autonomous systems?
Because they have to advertise the same subnet out. It's a scenario where we have 2 places where the 2 paths we can take to this network, and into 2 different data centers.
Okay, so the same
I
prefixes.
did the static route on a static route redistributed into BGP with and put a route, and I did a route map and set origin as IGP on the one side and origin complete on the other, and that's how I got it to prefer router 3. Say router 3.
Yeah, that would work. Yeah, because the origin is incomplete by default, and origin IGB is going to be preferred over origin incomplete.
Right. I just want to see if there's a better way to do that than, because because originally I added on our core switches, we had a static route that we redistributed into OSPF to the WAN router. That route was then advertised out via BGP. And then we would run in this scenario where, hey, when it would the kind of order of operations. So then if router 7 was also advertising it, but then until you had like a failover scenario, and then it would go, and the one side would keep learning it via OSPF instead of using its BGP route.
So do you control both router 3 and router 7 in this design?
Yes.
But they're multiple BGP ASs.
Yes. Yeah, so like I said, my solution was to do the origin.
Yeah, you could do the origin
APSLA, and then it drops out, and then the track route leaves, and then it's not advertised by BGP, and then the failover side is used, and then when it's back, when the IPSLA is in place again and working, then after 90 seconds it starts advertising, and since it's origin IGP is preferred.
Let me double check something with the path selection algorithm. I think one of the problems you'll run into is that the AS path is before the origin code. So if you're looking at a route that's originated by your own AS, and then you're also looking at one that's coming from a different AS, you would prefer the one that comes from your own AS because of the autonomous system path length. But is the solution working now?
It is. It is. I just wanted, I just wanted to talk, since we're talking, that's one of the things I worked a lot of time on, and just wanted to see what,
Yeah, it sounds like a viable solution, especially with the IPSLA tied to the static route.
Yeah. Yeah.
So is it,
The static, like now I have to have static routes on both my core switches and my WAN routers. The original design was going to be the static routes only on the core, and then redistributed into OSPF, and then the OSPF routes redistributed into BGP. But when I did that, that's when we ran into the failover scenario prefers OSPF even when it should fail back.
so it's advertised into OSPF and then redistributed into BGP.
Yep.
And when it goes down, you're preferring the OSP. I think that's an issue with the administrative distance.
But say router 7, it's got an OSPF route. It's going to have an OSPF route and a BGP route.
Right.
Okay. It should prefer the BGP route, but if say you lose it and then it comes, so it's learning the BGP route from router 3 and using it until I lose router 3 and we're not advertising anymore. So then it's using the OSPF route and we're advertising that out, and that OSPF route is getting advertised out of the network. The route from router 3 comes back up and we're advertising it back out in BGP. Router 7 it has that route, but it's preferring the OSPF route, even though it has so then it's just like it's ignoring the BGP route that's coming in from router 3.
This may be because you prefer your own origination. Prefer the path that was locally originated via network or aggregate, or the redistribute command. So if it's learning it through OSPF and then redistributing it into BGP locally, then it's going to prefer its own BGP route over somebody else's BGP route. So I think probably the static route with the IPSLA is going to be a better solution because it's going to be more deterministic than
that's what I
having
ended up
to do with BGP and OSPF.
That's actually what I ended up finding, and it actually works. We've had to do the failover a couple times now, so it actually does work. And my biggest thing was, hey, does it fail back? And it does. That's because I ran into that problem before I had with fault route where they are advertising it, and then the one is back up, but it's not preferred until you do like a soft clear, and then it would preferred. So that was a different scenario, but this, I just wanted, like I said, this solution is working. I just wanted to make sure that they did not miss, like, hey, is there a better solution in this case? But it sounds like what I came up with is predictable and actually works. So.
Yeah, static routes, a lot of people try to stay away from them, but there's some interesting problems you can solve with them.
I don't have, in this case, I don't have a choice but to do static routes because we're doing a static route to our firewall that has a static route to a vendor router. So that is kind of, and they don't support dynamic routing. So the static routers has to be this unfortunate solution. And that's why we do the IPSLA, because that's the only failover that they support. It's tracking the route by IPSLA.
Plus, it's job security because it's a much more complicated solution.
Yeah, it's like one of our most important. It's because we moved this application used to be on-prem, and we moved it to the cloud cloud. They call it the cloud of the vendor. It's just, they have it's a router connected to their network, so It's just it's like one of the most important things. So kind of like, hey, if we're tracking our failover scenario by ping, is kind of hurts a little inside, but
Yeah. Okay, one other thing that I can think of that you might run into a problem with this is that if you have any external OSPF routes that you're trying to redistribute into BGP. So let's say router 5 show run interface loopback 0. Okay, right now it's just advertising its loopback with the IP OSPF statement. And we should be able to ping to 150.1.7.7, which is router 7, sourced from 151.5.5. Okay, so the redistribution is working fine. Okay, we go to the loopback and say no IP OSPF 1 area 0. Instead, we're going to go to router OSPF 1 and redistribute connected subnets. Okay, so from router 3, if we look at the show IP route OSPF, we should see router 5's loopback as an external prefix. And then if we look at the show IP BGP 150.1.5.5, this should disappear here. Let me clear IPBGP. Let's see, can we still ping between the two of them? Yes, we can. The normal behavior here, though, is that when you redistribute BGP into OSPF or OSPF into BGP, it only takes the internal routes. So we would need to say redistribute OSPF 1 route map OSPF to BGP and then match internal routes and external routes. So it looks like in this version, that's the default, that it's matching both the internal and the external. But they must have changed this behavior because previously it only included the internal prefixes as we went from OSPF into BGP. Okay, what other specifics did you want to talk about with OSPF?
We talked about the tag. That's actually, about the tagging and the redistribution. Good question. Can we talk a little bit about like I've only done single area OSPF before, so I only have a single area OSPF network, so I'm not too familiar on a multi-area OSPF at all.
Okay, so we have OSPF area 0 that goes between 1, 3, and 5. And let's say that we have OSPF area 1 that goes between 5, 8, and 10. Okay, so on 5, let's go to gig 01.58, IP OSPF 1, area 1. Okay, on router 8, we're going to go into the OSPF process and just do a network statement for all subnets in area 1. And then same thing on router 10. So this is kind of cheating. It's just saying any interface that has an IP address, put it into area 1. Okay, let's look at the show IP OSPF neighbors. Okay, two-way state here means that there's not a transport problem, so they're just waiting to converge. Okay, loading to full. Let's look at the show IP route OSPF. And we have those external routes from 6 and 7, so the BGP redistribution is still working. Okay, let's ping 150.1.7.7, source 150.1.10.10. Okay, so we have connectivity end-to-end all the way to the remote BGP AS. Okay, the difference though here when we look at the show IP route OSPF is that the routes to like router 1 and router 3, these are now inter-area routes as opposed to intra-area routes. Basically what this means is that we're not performing shortest path first in order to reach those particular destinations. We're only running SPF up to the ABR, and then we're assuming that the ABR has a shortest path first in order to reach those particular neighbors. So if we look at the show IP OSPF border routers, our border router internally for intra-area routes is 150.1.5.5. So it's the router that's connecting area 0 to area 2, and we have a cost of 2 in order to reach them. Okay, if we look at from 5's perspective and show IP route 150.1.1.1, this is an intra-area route with a metric of 1001. So we take the metric that router 5 is reporting, and we add that to the metric that we have to the ABR. And then if we show IP route 150.1.1.1, we have a metric of 1003. So 1001 plus the metric of 2, which is to the ABR, in order to reach this destination. Okay, where you can see these in the database, the difference is that if we show IP OSPF database, these are the summary network link states. So this first one is LSA1. These are the routers within your own area. The network link states, these are the designated routers. And then the summary network link states, these are the inter-area routes. So it's telling us that router 5 is the ABR, the advertising router is 150.1.5.5. And then these are the inter-area routes that it's advertising. So as long as in my area, in area 1, I have a route to 150.1.5.5, then I implicitly have a route to 150.1.1.1 because we're assuming this guy has a shortest path tree in order to reach the particular destination. So if we were to look at the details, show IP OSPF database for the summary, of 150.1.1.1. We know about the metric, and it says the advertising router is 150.1.5.5. So we follow the shortest path tree to get to 150.1.5.5 and then use whatever metric it's reporting in order to add to our metric to get to the final destination. Okay, the other thing that you can do with this is that right now we're doing what's considered to be topology summarization. So we're cutting down on the amount of shortest path first runs that need to happen. We're only running SPF on these 3 nodes here. And then we're just following the existing shortest path either towards the ABR or to get to the ASBR. So someone that's doing redistribution in a different area, it says 150.1.1.1 is the originator of this type 5 LSA. We have this type 4 LSA that says to get to 150.1.1.1, go to 150.1.5.5. And 151.5.5 is a router in our own area. So we use the shortest path tree to get to 5, and then we use whatever cost that they're reporting inside this type 5 LSA in order to get to the final destination. So we can also see this when we looked at the show IP OSPF border routers. We know that router 1 and router 3 are doing redistribution, and they are ASBRs. We have a cost of 1,002 to get to these destinations. So if we look at the show IP route OSPF and look at the external routes, let's say to router 6, show IP route 150.1.6.6, we have what's called the forward metric. Okay, the forward metric is what's the metric to get to the ASBR, and then what is the metric that the ASBR is reporting in. So if we had multiple routes to the same destination and we had a tie in the metric, then we would fall back to this forward metric as the tiebreaker between the 2 of them. But basically what the whole process is here, it's different steps in recursion, that we have one route pointing at the other, which points at the other towards our final destination. So your summary network link state is always going to point at an advertising router that's in your area. Then the same with the externals. The external is advertised by 150.1.1.1. So if we show IP OSPF database for the router 150.1.1.1, this is not a router in our own area. So this is where LSA 5 is going to point back to LSA 4. So it's saying to get to router 1, router 5 has reachability to that. So if we show IP OSPF database for the summary, for the ASBR summary 150.1.1.1, it says to get there, we're going to use the advertising router 150.1.5.5. And if we show IP OSPF database for the router 150.1.5.5, this is in our area 1. So based on how the links are connected together, we would have a shortest path tree that gets us to router 5. Then we're going to use whatever router 5's metric is to get to router 1, and then add that to the external cost in order to get to the final destination. But what's kind of interesting about this is that it doesn't change the number of routes that you have in the database. So if we were in area 0, the output here would look the same, except these would be O routes as opposed to OIA routes. What it's saving is how many times do you need to run SPF, or how complicated is the graph behind the scenes when we're actually running SPF. Okay, if we wanted to take this one step further, this is where the stub areas would come in.
No, that's what actually, that was the question I was going to ask. So awesome.
So if we go to router OSPF 1 and say area 1 stub, okay, that's on 10, 8, and 5. So we need to agree on all three of these routers. Area 1 stub. Router OSPF 1, area 1 stub. Okay, and if we look at the change in the database, show IP OSPF database, we no longer have the type 4 LSAs, the summary ASBRs, and we no longer have the external routes. But what got replaced with this is a default route towards the ABR. So the idea was that previously we were going towards our ABR for all of the external destinations. We were going towards our ABR in order to get to the ASBRs, to the ones that were doing the redistribution. So we could kind of summarize this all together with just a default route towards the ABR, and we're still going to have the same result in connectivity. So if we show IP route OSPF, we now will see the intra-area routes and the inter-area routes, but we're not going to see any of the external routes.
You get the follow that default.
And it's going to default, correct? Yeah, so we should still be able to reach the destination, which is that external BGP router. But if we look at the show IP route 150.1.7.7, it says we don't have a route to it. If we show IPsec for 150.1.7.7, it says the longest match is our default route that's going towards router 5 ultimately.
What would be the disadvantage of doing the stub like this as opposed to not? Or
there's really no disadvantage as long as you don't have multiple exits out of the area. So based on the way that our topology looks, since router 5 is the only exit point out of the area, then there's no disadvantage of making this into a stub area.
So if you had another router there, you would probably then you would probably not want to do stub.
Correct. Correct. I mean, you could do multiple default routes where they're load balancing between the two. But if you want to do some sort of traffic engineering based on an individual specific subnet, then you lose that ability if you're doing the stub areas. So right now, again, they have the intra-area routes plus the inter-area routes. But for all of these inter-area routes, if we show IP OSPF database, and we look at the summary network link state, so these are the routes in different areas, it says use the shortest path tree to router 5 in order to get out of the area. So for 1's loopback, for 3's loopback, for these other prefixes, use the shortest path tree to router 5. So we could go one step further and summarize all of these to just the default route because we only have one exit point out of the area anyways. Okay, this would be if we went under the OSPF process and we said area 1 stub no summary, which is now a totally stubby area. So in the totally stubby area, it removes your LSA 4 and 5 like the stub area, but it also removes your LSA 3s. So if we look under summary network link states, previously we had 1, 2, 3, 4, 5 specific routes. Now under summary network link states, we just have a default route. So if we look at the show IP route OSPF, we have routes in our own area, and then we have just a default route to get to the ABR. In any case, we still have reachability though. So it doesn't affect the connectivity. It's just replacing The more specific route, like to router 1 loopback,
It's got to go to that router anyway. That's its only way to go. So
exactly. It's got to go to that router anyways. So it doesn't make sense for us to have the more specific routes and not have just a default route. But we can still reach it if we ping 150.1.1.1. We have reachability to the destinations. We're just following a default route as opposed to following more specific routes. Okay, the only one real disadvantage of this is that if you had some other external domain, so let's say we had like EdgeRP here, into the stub area and the totally stubby area, you're not allowed to do redistribution. So this is what the not so stubby area and the not so stubby area totally stubby. So NSSA no summary. These are if you need to do redistribution in the stub area. They introduce a new special type of LSA, LSA 7, that gets converted into LSA 5 as you go from area 1 into area 0. But we should see, like if we go to router 10 and go under OSPF and say redistribute connected, it should give us an error message. Router is currently in ASBR while only having one area, which is a stub area. So this is not a supported config. So likewise, if you had like a static route and you needed to redistribute the static route, then you would have to make it a not so stubby area as opposed to a regular stub area.
makes sense.
And one of the best resources on this to get more information is Routing TCP/IP Volume 1.
Okay.
By Jeff Doyle.
Got it. I actually have a hardcover of that, hardbound copy of that book. So
Yeah, so this one and Volume 2, you could think of these as kind of the routing Bibles for Cisco. And he does some pretty good coverage of the stub areas and the filters and so on and so forth. Okay, any last questions for me, Vince, before
Nope.
we finish up
Nope.
here?
No, this has been great.
Yeah, so if you come up with anything else, feel free to shoot me an email. More than happy to help out remotely.
Awesome. It was great. It was great. You know, it confirmed some things that I thought I knew, and so that's awesome.
Okay,
And
great.
you know,
Well,
I've never, like the multi-area stuff with NSSA and all those things. I haven't had to do that in production or anything like that. And so you know, so now I want to learn more about it. So
great. Great. Well, it was great talking to you. Thanks for coming out to the networking week and entering the contest.
okay, I'm on your guys' site all the time for learning stuff. So I'm logged in probably every day.
Well, that's great. I hope we can help you out in your continued studies.